Welcome, my friends. In this video, I'll be covering section 7.3, the confidence interval for the difference in two proportions. We will be doing this confidence interval as a post hoc to the chi-square test, meaning a follow-up after we've completed a chi-square test. Let's talk about the confidence interval for the difference in proportions. For this confidence interval, we want to estimate how much larger or smaller one proportion or percentage is compared to another. For example, let's say we are comparing the percentage of vegetarians in the United States and India. We could say that P1 is the population proportion of vegetarians in the United States, and P2 is the population proportion of vegetarians in India. P1 minus P2 is what the confidence interval is for, which represents how much higher or lower the percentage of vegetarians is in the United States compared to India. Now think for a second about what it means to subtract two numbers. When we subtract two numbers, the result is telling us how much larger or smaller one value is compared to the other. If we subtract two numbers and we get a positive number, that must mean that the first number was larger than the second. If we subtract two numbers and we get a negative number, that must mean the first number is smaller than the second. So for example, let's say we have a 95% confidence interval for the difference in two proportions, and we get 0.02 to 0.06. That would mean that we are 95% sure that the United States has anywhere from 2 percentage points all the way up to 6 percentage points more vegetarians than India. An unlikely result if you know anything about the percentage of vegetarians in these two countries. A more likely result would be something like this. So let's say we have negative numbers in our interval. Let's say we have negative 0.08 to negative 0.03. Well, remember that the negative numbers actually mean that the first proportion is smaller than the second proportion. So we would say that we are 95% sure that the United States has anywhere from 3% to 8% less vegetarians than India. So the main thing to keep in mind here is that any of the numbers we have in our confidence interval are telling us the comparison value, how much larger or smaller one proportion is compared to the other. Here's the formula to calculate the confidence interval for the difference in two proportions, which is quite calculation intensive. So due to the calculation intensive nature of this formula, in this class I'm going to be using the TI-84 calculator function called 2propzint, which utilizes this formula. We can visualize the confidence interval on the number line. We are trying to estimate the difference in the two population proportions, and our best estimate for that, sometimes called the point estimate, will be the difference in sample proportions. Somewhere below that we will have our lower bound, and somewhere above that we will have our upper bound, and the distance between those will be the margin of error, everything after the plus or minus in the formula. Don't worry, you won't have to plug into this formula if you're one of my students because we are going to be utilizing the TI-84 calculator, but this is how it will be done. Now, we've done one sample confidence intervals in a separate chapter, and I have my own separate confidence interval interpretation specifically for the two sample confidence intervals. So here it is. It says we are C% confident that either population mean 1 or population proportion 1 is anywhere from the absolute value or positive version of the lower bound to the absolute value or positive version of the upper bound, either larger or smaller than the population mean number 2 or population proportion number 2. Note that I've written this in general to work for either proportions or means, and we will cover the confidence interval for two means in a separate video. Now, the reason why we have the absolute value or positive version of the upper and lower bounds here is because the word larger or smaller is going to be doing the work of the positive or negative sign. So if you have positive upper and lower bounds, that means you are C% confident the first mean is, or first proportion is larger than the second, so you'd say larger. Or if you had negative upper and lower bounds, then you would say smaller. Now, if you end up having different signs, which won't happen that often in this class, like maybe you have a negative and a positive for your lower and upper bounds, then you'd have to kind of distribute these different terms. So it's not really a perfect template here. So you'd have to say the lower bound smaller all the way up to the upper bound larger, potentially, or some kind of combination of that. Okay, but we'll look at examples. Make sure you can describe the population mean or proportion as it relates to your specific problem. So don't just leave it as population proportion 1 and 2. You're going to substitute in specifically what your proportion is for your problem. So for example, let's say that our 90% confidence interval came out to negative 0.08 to negative 0.03 for the difference in the proportion of vegetarians in the United States and India. Then we would say we are C% confident, or 90% confident, that the population proportion 1, which is the population proportion of vegetarians in the United States, is anywhere from 0.03 to 0.08. And here's another place where you could kind of switch things around here. These are both negative, first of all, so that's why I have dropped the negative sign. We need the absolute value of those two. And if they're negative, I like to actually write this one first, the second one first. So it does say lower bound and upper bound, but I've written the upper bound actually technically first because it's smaller in absolute terms. So from 0.03 to 0.08, and then I use the word smaller because we had negative numbers here. So the word smaller is doing the work of the negatives. Than the population proportion of vegetarians in India. So altogether, we don't know for sure what the difference in proportions of vegetarians is in the United States and India, but based on this sample, we're able to say with, let's say, 90% confidence that it's anywhere from 0.03 to 0.08 smaller than in India. Now, of course, if you had positive numbers, then you would use larger instead of smaller, which it says right here. Or you don't always necessarily have to use the words larger or smaller. You can kind of substitute any word that kind of works in the problem to represent this. So you could say bigger. You could sometimes say if you had something that was in terms of like time and like finishing a race, then actually smaller would be like running the race faster. So in many cases, you can kind of substitute different words in here. So it's a little bit flexible. This template isn't perfect, but it's just a kind of way to get you started with writing some of these confidence interval interpretations. Okay, one other thing to mention here is that there are really three different possible results for confidence interval, or the difference in two proportions, in terms of the signs that you get in the interval. And we kind of already mentioned this a little bit. So if you have both values in your interval are positive, then that means for everywhere inside your interval, you're estimating that the first population proportion is larger than the second. Remember that when we subtract two values, if we get a positive number, that must mean that the first number was smaller than the second. That's the only way when you subtract two numbers to get something positive, is if the first number was larger than the second. So if you get a confidence interval, well, every single number in that interval is positive, then that indicates that we are C% confident, whatever your confidence level is, that the first population proportion is larger than the second population proportion. So this is a way you can use your confidence interval to kind of state with some degree of confidence that there's maybe a difference or not a difference between your proportions. If you have two negative numbers, then it's just the opposite. The only way to get a negative number when you subtract two numbers is if the first number was actually smaller than the second. So then in that case, we would be C% confident that the first population proportion is smaller than the second. Or you could have the case where you have one positive and one negative. So that kind of means that you are crossing over zero in your confidence interval. So you have, if you're going from negative to positive, that means the number zero is in there somewhere. And think about the number zero and what that would mean. Well, the only way to subtract two numbers and to get zero would be if those two numbers are the same, right? So if those two numbers are the same, we would get zero. And zero is a possible kind of result inside this interval. And zero would mean there's no difference in the two proportions, right? So if this is the case, then we would say we cannot conclude whether or not the first population proportion is larger or smaller than the second, because zero is contained in the interval. It doesn't matter if it's kind of lopsided and if there's more negatives than positives. No, we always just say that if we have the mixed signal here, we cannot conclude with any confidence here that there is a difference between those two proportions. Okay, in this class, we're only going to be completing this confidence interval for two proportions as a follow-up, sometimes called a post hoc, for the chi-square test. And we will only do this when we reject the null hypothesis. So you might remember in the chi-square test, the null hypothesis is that there's no association between the two variables, and the alternative is that there is an association. So if we reject the null hypothesis and conclude that there is an association between the variables, we're going to be able to estimate like how associated they are, what the difference is based on this confidence interval, right? And we're going to be using the Fred technique that we've used many different times here. So first, we're going to formulate the problem for the confidence interval and the difference in proportions. Now, we've already done a number of those things in the chi-square test, and since we're doing this as a follow-up for the chi-square test, the only additional thing we're going to have to do here is describe the two proportions that we're going to be comparing. Now, theoretically, for a chi-square test, there could be more than two proportions, but we will only do it when there are two. There could be 3 or 4, and you have to technically do even more comparisons. But the only examples that I'm going to use are when there's only two proportions. Then next, we typically would review conditions, but since we're doing this as a post hoc to the chi-square test, the conditions would have already been checked for the chi-square test, which will suffice to do this confidence interval. Next, we can go ahead and execute the calculations, which would be either using that formula, which was pretty nasty from before, or if you're one of my students, we're going to be using the TI-84 calculator 2 prop z interval function. And then finally, we will draw conclusions by writing a conclusion statement that has that form that we looked at from before. So let's go ahead and look at a full example, and we're going to do a truly full example in that we're going to do the chi-square test first, and then we're going to do the post hoc as the confidence interval for the difference in two proportions. So this problem says the following table shows the number of passing students in online and in-person versions of the same class at a university. So they could either take an online class or an in-person version of the same class, and then they could also either pass the class or fail the class, and that's listed in this table. And they're telling us here to use this information to test if there's an association between the variables at a 5% level of significance, and then, if necessary, being if we reject the null hypothesis, construct a 95% confidence interval for the difference in two proportions. So the first step for a chi-square test would be to formulate the problem, the F in Fred. And in this case, the population would be all students at this university that we are sampling from. The sample would be the 1,573 students that we sampled, that is represented in this table. The variables that we have collected are whether or not, the type of class that they are taking, either online or in person, class format, and then the pass or fail status. And then we can go ahead and we can set up the null and alternative hypotheses. So you might remember for a chi-square test, the null hypothesis is that your two variables, in this case class format and pass-fail status, are not associated. And the alternative is that they are associated. So the exact same thing, class format and pass-fail status are associated. Next, we can go ahead and we can execute the calculations. So if we grabbed our TI-84 calculator, you may remember that we can put these numbers into the matrix. So we can go to second matrix, and then we can go ahead and we can go to edit. And then I'm going to go ahead and make this a 2x2. And I'm going to put in all the numbers in the inside of the table. Okay, I don't have to put in any of the totals. I just have to put in the inside of the table. And then I can go to stat, arrow over to tests, and then I can scroll down to the chi-square test. Here it is. I shouldn't have to change anything here. I can just go right down and calculate, and it's going to give me the information that I need, which I have also copied down here. 26.04. 26.04, p-value of 3.3 times 10 to the negative 7. That's what this means. It's scientific notation. So this is the output that we get on the calculator. Okay, so then we have to make our decision to either reject or fail to reject our null hypothesis. And hopefully you're familiar with how to read this. This basically says move your decimal place 7 places to the left. So the decimal place is right here. The E-7 says move the decimal place 1, 2, 3. You'd have to move it 7 places to the left. And actually, that's going to give you 6 zeros before you have this number. You're going to have 1, 2, 3, 4, 5, 6 zeros, right? So if I move this 1, 2, 3, 4, 5, 6, 7, you would see it's back in the same place that it was. And I've lopped off the rest of the decimals here. I just put 6 zeros and then the 3. So anytime you're reading this kind of scientific notation, it's just 0 point, and then you have 1 less 0 than this number, and then the number that's there. Okay, so this is less than or equal to the level of significance. So think to yourself for a second, if you remember back to hypothesis testing, what does it mean when your p-value is less than or equal to your level of significance? Well, as the saying goes, if the p-value is high, the null will fly, or if the p-value is low, the null has to go. So in this case, the p-value is low, so the null has to go, and we're going to be rejecting the null hypothesis. And if you wanted the image here, you could see that our chi-square test statistic of 26.04 kind of goes at the cutoff of the tail here, and the probability to the right of that is the p-value, which is a very small probability, should probably be smaller on the picture. But basically this says that the chance of getting the results that we got, assuming that class format and pass-fail status were not associated, is extremely low. There's only a 0.000003 chance of that happening. So we're going to reject that, and then we're going to conclude that class format and pass-fail status are indeed associated. Now, we skipped the review conditions step because we had to do the execute calculations first if we're going to do it on the calculator. And you might remember that once you run this test, you can go back into the matrix. So I can go a second matrix, and I can scroll back twice to the right, and then I can go and look at matrix B. And it has exported the expected value matrix into the matrix B. And one of the conditions all relate to these values. And basically these values have to be, if all the values are greater than 5, then you're good. The things that you're checking here is that no expected cell count is less than 1. None of those values are less than 1. And also that no more than 20% of them are less than 5. Well, none of them are less than 5 either. They're all plenty large enough, right? Remember, these numbers are what you would expect this table to look like if class format and pass-fail status were not associated. So if they were not associated, you would expect to have these numbers here, but we actually have these numbers here. So you can start to see why we rejected the null hypothesis, right? 81 compared to 113, that's quite a bit different. 89 compared to 58, that's quite a bit different, right? So since those numbers were so much different, it kind of was leading us to reject our null hypothesis. Okay, so then we can go ahead and we can draw our conclusions for the chi-square test. And there's a template for conclusions for hypothesis tests. It's at the alpha % level of significance. In this case, it's 5%. There is enough evidence. Remember, you say is when you reject the null hypothesis, or you say is not when you fail to reject. In this case, we did reject, so we say there is enough evidence to suggest that class format and pass-fail status are associated for this class at this university, right? So this is just restating our alternative hypothesis, right? So all that, last 5 minutes or whatever, all that stuff should have been review based on the previous video. So I know I went a little bit faster on that stuff, but that should be familiar to you at this point. And now we kind of get to do the new stuff. So since we rejected the null hypothesis, and only because we rejected it, if we didn't reject the null hypothesis, we'd stop there. But since we rejected the null hypothesis, we think there is an association between these two variables. So we want to get a little more detail about how they are associated. This is kind of broad. They're associated. How are they associated, right? So now we're going to tell more specifically how they're associated by doing the confidence interval for the difference, not the difference, for the difference in the two proportions. So let's go ahead and do that. So first we have to formulate the problem for the confidence interval for two proportions, which the only additional step that we have to do here is to define the two population proportions. And you should always do this based on the rows of the table, since you might remember that we always set these tables up so that the rows are representing the explanatory variable. Our two proportions are going to be based on the rows. So it's basically going to be the proportion of people who pass for the online class and the proportion of people who pass for the in-person class in the population. So let P1 represent the proportion of all students at this university who would theoretically pass the online version of the class. I say theoretically because they're not all taking this class, but the population relates to everyone at the university. And then P2 would represent the proportion of all students at this university who would theoretically pass the said online, but I just changed it to in-person version of this class. And that's really all we have to do for the formulate the problem step. And we don't have to review conditions because we already reviewed conditions in terms of the chi-square test. So we can go right ahead to our step 3 here. So I'm saying we don't really have to do this because we already did this. So we can move right on to the execute calculations step. Now, before we go to the TI-84 calculator, which is how we're going to do this step, I would write down some of the information here and kind of the symbols that go along with those, because it's going to make it easier when you eventually go to the TI-84 calculator. So let's say that our first sample is going to represent the online students, and let's say that our second sample is going to represent the in-person students. And we can see here that for the online students, the total number of students was 750. So that's our sample size for the online students. So that's going to be N1. And we had 637 of those people pass. So that is going to be our X1. Now from those two values, we could calculate P hat 1, the sample proportion number 1. But if we're doing this on the calculator, it's not really necessary to do that. So I'm not going to do that at this point. I'm just going to write out this as kind of our main information for sample number 1. Now we can do the same thing for sample number 2. Our sample size is 823. And we had 765 of those individuals pass. Okay, and then at this stage, you would be ready to go to the TI-84 calculator and generate the confidence interval. Now, I'm going to show you here the by hand work, but I'm not going to go through it in detail, but I'm just going to show you what it would look like if we were to do this by hand using the formula. It would look like this. So here's the formula. The first thing you'd have to do is find the z-score, and you may be familiar with how to find this. You can find it either with a probability table or with the inverse norm function on the calculator. The area to the left would be the 95% in the middle, plus there's a 2.5 in the tail, is where we're getting this 0.975. You'd have to calculate the two p-hats by dividing each x over n, find each q hat by taking 1 minus each p hat, and plug everything into the formula, which is, not a very nice formula, and it can take a lot of work and a lot of time, and you got to be really careful because it's easy to, accidentally type something in wrong. But once you're all said and done with this, you should get these two numbers, the first one when you subtract, and the second one when you add. But like I said here, the focus of this video is not going to be the calculation. It's more going to be using the calculator. So if we wanted to do this on the calculator, let me show you how you could do that. Let's get out of this. So to get out of this screen, I can press second and then quit. And this is in the same menu that chi-square test was. So if we go to stat, and then we arrow twice to tests, move this to the right because I'm going to need some of those numbers. And you got to be really careful here because a lot of the options here look pretty similar. The one that we need is not the 2prop_z test. It's a further one down. It's called 2prop_z int. 2prop_z test is a hypothesis test, but we're doing actually a confidence interval right now. So we're going to do this one. And then we can go ahead and type in the numbers. So 637 is our x1. Our n1 is 750. X2 is 765. And our N2 is 823. The confidence level, they told us, is 95%. We don't have to do an adjustment for this. This is asking literally for the confidence level. We don't have to do like 0.975 like we might do in inverse norm or inverse t. This is literally asking for the confidence level. Just make sure you put it in decimal form, so 0.95. Go ahead and calculate, and it's going to give us a whole bunch of information. It's going to give us the p-hats as well as the two bounds of our interval, which are the same numbers that I had here based on the formula a second ago, right? Negative 0.1112 and negative 0.0492. So it saves you quite a bit of time just plugging in these numbers as long as you can remember how to get there on the calculator. So here we have that information. And then we can go ahead and we can move to the last step of the confidence interval, which is to write our sentence for conclusion. So using the template that was introduced earlier, we can say that we are 95% confident, that was our confidence level, that population proportion number 1, which is the proportion of passing students for the online version of the class, is anywhere from, and now I'm going to state the two bounds, and since I had negatives, I'm going to write the second one first, 0.0492 up to 0.1112, smaller since they were negative, than the population proportion of passing students for the in-person version of this class. You could also write these as percentages if you wanted to. Technically, you might want to write them as like percentage points. So you could say that anywhere from 4.92 percentage points to 11.12 percentage points smaller. Basically, the students in the online class are not passing quite as often, anywhere from like 5% to 11% less as compared to the in-person class. So now, the very first step was to do the chi-square test, and we determined that the two variables were associated. And now, using the confidence interval for the two proportions, we got a little bit more detail. Not only do we know that there's an association here, we now know that the online students are passing at a lower rate, and the rate is anywhere from like 5% to 11% smaller. All right, so here is a problem for you to try. So it says the following table shows the proportion of correct orders from a sample of orders at Taco Bell and Wendy's. And assume that we've already done the chi-square test, and that resulted in the null hypothesis being rejected, basically saying that there is an association between which restaurant you go to and whether or not the order is correct. So basically, one of these two places is more accurate on average in terms of getting your order correct than the other, right? But then the question is, by how much and which one, right? So go ahead and construct a 99% confidence interval for the difference in the proportion of correct orders between these two places. So first formulate the problem. So determine what P1 and P2 is going to be. And then go ahead and you can skip the review conditions. You can go right to execute the calculations. Write down X and N for the two samples, just like we did in the last problem. Plug those numbers into your calculator, get your result, and then finally write a sentence describing your conclusion. All right, that's all I had to talk about in this video, so I will see you in the next one.